So we're talking about thermochemistry, thermodynamics. We'll start with the first law of thermodynamics. There is no free lunch. That's not the official statement. The official statement of the first law of thermodynamics is given right here. The total amount of energy in the universe is constant. Thermodynamics, we're looking at energy and its interconversions between different forms. And what the first law of thermodynamics tells us is that you can never design a system, a device that will produce energy without using some source of energy. You can't get something for nothing. And so that's where there is no free lunch comes from. Because yes, at the school my children used to go to, everyone qualified for free lunch. Does that mean their lunch is actually free? No, it means that the children don't pay for it. The parents don't pay for it directly. But somebody has to pay for it, right? That would be the government. So you can't get something for nothing. That's why we have taxes. Taxes. Yeah. Okay, so energy flow. Conservation of energy means that when you add up all the energy changes, they have to add up to zero. If something loses energy, something else gains energy. Sometimes it's a little tricky to track down all the changes that are happening. Thankfully, in Chem 1A, we can avoid most of the tricky situations. So we looked at an energy gauge like this before when we talked about the system and the surroundings. So if the system is losing energy, it's going from half full to a quarter full, then the surroundings must be gaining an equal amount of energy. So one is losing, one is gaining. I think of energy as being a lot like money. In a financial transaction, money doesn't disappear. If I pay you $5, you get $5. My loss is equal to your gain. Okay, that's what happens with energy. Now, sometimes it looks like energy's or money's being lost, because, the college pays me, but the amount they pay out, I don't receive all of it, right? Some of it goes to the government for taxes and for retirement and all these other little things. But if you add up all those things, my net pay and the taxes and all those other things, all of those things add up to equal what the college is putting out. So it's not like money is being created or destroyed. Now, don't tell me about the treasury and how they can print more money. We're ignoring that part. Okay, there's no energy treasury where they print more energy. So the total energy of the universe. Delta is, this is the Greek letter delta, which is its version of D. Delta means change in. So delta energy means the change in energy of the universe. And by convention, delta is always the final amount, stupid pointer, the final amount minus the initial amount. Final minus initial. So the change in energy of the universe equals zero. That means that the change in energy for the system plus the change in energy for the surroundings has to add up to zero. Therefore, one is positive and one is negative. Everybody okay with that? Very important basic idea. Well, there's different kinds of energy. So what we call internal energy, and that is symbolized with a capital E, that's the sum of the kinetic and potential energies of all the particles in that system, whatever we define the system as. Okay? So it's the total amount of energy, both kinetic and potential. The change in energy only depends on the final amount and the beginning amount. It doesn't matter how the change occurred. It just matters where it started and where it ended. So we say that energy change is a state function. So a state function means that the result only depends on the initial and final conditions. It doesn't depend on the process used. And that's an important idea. So the change in internal energy for a system equals the energy of the final minus the energy of the initial. Or when we're talking about a reaction, the change in energy for the reaction equals the energy of the products minus the energy of the reactants. So if the products have more energy than the reactants did, then overall there will be a positive change in energy. So let's talk more about what this idea of a state function is. So let's think about climbing a mountain. So here's a mountain, and there are two paths that you can take. You can climb path A, which is 12 miles long and wiggles around, but it's not terribly steep, 12 miles. Or you can head straight up the mountain. That's only 5 miles, but it's hecka steep, right? It's just really hard to climb up there. So how you get up there is not a state function, but the change in elevation is a state function. If you start, everybody's starting here at 0 feet above sea level, and everybody's getting to the top. At the end of their hike, they are at 10,000 feet. The change in elevation is 10,000 feet. It doesn't matter which path you took. The change in elevation is the same. Does that make sense? Change in elevation is a state function. You could have taken a helicopter to the top of the mountain. That'd be a lot easier, right? You could have flown around the world and come back and landed on top of the mountain. You would have traveled tremendously farther than even the person that took the windy path. But the change in elevation is the same. Do you get it? Okay, so energy change is a state function. How it happens doesn't matter, just the final and the initial. So we use energy diagrams in an attempt to visualize what's going on here. One of the challenges of learning chemistry is that a lot of it is very abstract. I'm a visual person. I need to be able to see something. And so we draw pictures for ourselves. I paint pictures in my mind of what these things are doing, and that helps me to understand what's going on. So an energy diagram is just a visual picture of what's happening with the energy. So this is the energy diagram right here. So we represent the internal energy of the system as increasing as we go up. And that's typical for graphing things. At the top of the paper is more positive and the bottom's more negative. So here are the products and here are the reactants. This is the chemical reaction we're looking at. Carbon dioxide decomposing into carbon and oxygen. So the reactant has a low internal energy, and after the reaction, the products have a higher internal energy. So the change in energy for this reaction is that the amount of energy present in those substances went up. That means that energy had to come from somewhere, because it doesn't just get created. So the change in energy for this reaction is positive because energy came into it. That means that the change in the energy for the surroundings must be negative because the energy left. And the amount of energy given up by the surroundings has to equal the amount of energy absorbed by the system. So it's like money. You know, you think about, you look at your banking app and you pull up the transactions, and some of them are negative and some of them are positive. What does a negative transaction mean? It means that money left your account, right? And you kind of feel negative about that. I'd rather it didn't. And then the positives are money coming into your account, and you're like, yay, I got paid, right? So energy coming in is positive, energy going out is negative, just like we view money. Any questions? If we run this reaction the other way, where we're combining the carbon and the oxygen to make CO2, CO2 has a lower internal energy than the carbon and the oxygen do. Carbon and oxygen have higher. So here the reactants were higher in energy, and the products are lower. So the change in energy is negative. The energy of the system went down. It lost energy. Energy left. Where did the energy go? It went into the surroundings, the rest of the universe. So the change in energy for the system here is negative. The change in energy for the surroundings is positive. And these energies are equal. They're just opposite in sign. So if I pay someone $5, they receive $5. The $5, whether it's positive or negative, depends on whether you're looking at the buyer or the seller, right? So the change in energy, whether it's positive or negative, depends on, are you looking at the system or the surroundings? It's positive for one, negative for the other. because of how we define the system and the surroundings. The system is whatever we define as what we're looking at, and the surroundings is the rest of the universe. If energy flows out of a system, it has to go into the surroundings. It can't go into some nether world. So energy flowing out of the system is negative. Energy flowing into the system is positive. I'm sorry, energy flowing into the surroundings then would be positive. So the energy gained by the surroundings is equal to the energy lost by the system. The signs are just different. Okay, it's like transferring money from a checking account to a savings account. It's negative for one and positive for the other. So energy can be exchanged between different objects through two processes, heat and work. Heat is the transfer of energy based on temperature changes, and work is defined as a force exerted through a distance. Right? So those are the two ways that energy can be transferred. So we can have heat or work, or we can have both of them happening at the same time. So we represent heat with a lowercase q. Don't know why, but we do. And work is a lowercase w. That makes a little more sense. So q and w, heat and work. Those are not state functions. Okay? Those do depend on the process. So when you're climbing that mountain, the change in elevation is a state function, but the distance you traveled is not a state function. That will depend on which path you took, right? So the change in energy has to equal the heat plus the work. Those are the two processes by which energy can be transferred to something else. So heat, if the heat is positive, that means the system is gaining thermal energy. If it's negative, the system loses thermal energy. W, work, positive work is being done on the system, negative work is being done by the system. Okay? So that one's a little trickier to understand. Think of someone giving you a massage. There are people who get paid to give massages, right? So if you are receiving the massage, if the massage work is being done on you, that's a very positive thing, right? It feels good to have someone massage your shoulders. If you are massaging someone else, you're putting out work. You're working, it's hard, it's not so satisfying, and so that's a negative. Okay, so work that you're doing is negative. Work being done on you or for you is positive. So we're going to look at the pool table again. So here we have that billiard ball, the cue ball, and it's rolling across the table, and it's going to hit this purple ball. So this has an initial kinetic energy. Let's say it's 5 joules. That kinetic energy depends on its mass and its velocity. So it's rolling across the table. Now this is a real pool table, and so we know that as the ball rolls, it's going to slow down, right? Because there's friction. So as it rolls across, it's going to lose a small amount of its energy to heat. You're not going to notice that feeling the pool table afterwards. It's not going to feel hot, but it is a small amount that's lost to heat. So as it rolls, it loses some energy. It slows down a little bit. When it collides, then there's kinetic energy at collision. So when it collides, it still has 4.5 joules of energy left. And that energy is transferred to the purple ball. So we have work, which is the movement of this ball across the table, and it's applying that force to the other ball. So the work for the white ball is negative 4.5 joules. At this collision, it lost the kinetic energy it had. Q is minus 0.5 joules. That's the amount of heat it lost to friction as it was rolling. So the total loss in energy for the white ball is negative 5 joules. It started with 5 joules, and as it rolled across and collided, it lost all of its energy. So the energy after the collision is 0. Does that make sense? So there's heat and there's work. So that's if the table is smooth, a good pool table, right? If the table is rough, maybe it's been abused, left out in the rain or something, it's just really rough and bumpy, there's a lot more friction as the ball rolls. So the ball, as it starts out with 5 joules of kinetic energy again, as it rolls across, now it loses 3 joules to heat through the friction of rolling. It only has 2 joules of kinetic energy at collision that it can transfer to the other ball. The change in energy for that ball, though, is still negative 5 joules. But the process is different. 2 of those joules were lost to work in the form of heat, in the form of thermal energy lost. And no, sorry, I was thinking that was backwards. 3 joules are lost to heat from friction, and 2 joules are lost as doing work. The overall change in energy is the same. The cue ball started with 5 joules, it has 0 joules at the end. But the process is different. Q, heat, and W, work, do depend on the process. The overall change in energy does not. Any questions? I'm kind of repeating myself, but that's intentional because it takes a few times. So we saw that the change in energy for the cue ball was the same on both the rough table and the smooth table. But the work and the heat are not. That's because the change in internal energy is a state function. Depends only on the velocity of the white ball before and after the collision. The sum of heat and work is the same in both examples. The sum is equal to the change in internal energy. But Q and W are not the same. They just add up to the same thing. The energy lost by the cue ball is equal to the energy gained by the surroundings. Now, the surroundings there is not just the purple ball. The purple ball gains some of the energy, but the pool table gains some of the energy as well. The surroundings is everything but the white ball. These numbers are equal. The sign is different because one's giving and one's receiving. Any questions? So heat is the transfer of thermal energy between a system and the surroundings, and that is based on a difference in temperature. Temperature is the measure of the thermal energy within a sample. So a measure of the average kinetic energy, kinetic thermal energy. So heat will always flow from something that's higher in temperature to lower in temperature, and it will continue to do so until they reach the same temperature. That's called thermal equilibrium, and then there's no additional net transfer of heat. And so we can observe this with various objects, right? If you put, what's a good example? Okay, so my husband's Japanese, and so rice is a very important part of my family's diet. They get grumpy if they don't have white, sticky rice several times a week. And so there's always leftover rice, and then how to make the leftover rice appealing to the child. And so kind of by accident, I came up with this method of heating up older rice, and it's called water rice. And so you take the leftover rice, and you get some boiling water, and you pour boiling water on the leftover rice, and you wait a little bit, and thermal equilibrium is achieved. The cold rice warms up, the boiling water cools down, and then you drain the water off. And they know it's water rice because it's wet, right? And then one of them used to put Parmesan cheese on that. Ew, yes. He called it sprinkles. Anyway, thermal equilibrium, though. The hot water warms up the cold rice. We know from experience that these things happen, right? A warm thing will cool down, a cold thing will warm up, and they'll end up at the same temperature. Okay. So let's put these ideas into practice. A cylinder and piston assembly, and we're defining that as the system, the cylinder and the piston. It's warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during expansion, what is the value of delta E? What is the change in internal energy for the system, the cylinder and piston? So this is how we think about that. The change in energy is going to equal heat plus work, Q plus W. So the problem is telling us the system absorbs 559 joules of heat. So that's Q, that's heat. It absorbs that much heat. So you put yourself in place of the system and say, I'm absorbing heat. That's like money coming in, right? Heat coming in. Is that positive or negative? That's positive. So this is positive. And I'm going to put a plus sign there just to emphasize that it's positive. And then it says it does work. So the W is 488 joules. So the system is doing work. Is that positive or negative? That's negative. It's doing work on something else or for something else. Work is positive if somebody's working on you or working for you. Hey, you're doing my stuff for me. I really feel good about this. Here, I'm doing your stuff for you. That's a negative for me, a positive for you. So we have to identify the signs on Q and W. And then the change in energy, delta E, is just the sum of those. So Q is 559, and we add W, but W is negative. So that's one way to do it. Yeah, this is trouble opening my calculator. So 559 minus 488. So that equals 71. So the change in energy for the cylinder piston assembly is positive 71 joules. So overall it gained energy. Any questions?